All right, let's begin. So, we continue on 9.6, finishing arc length, and the second part of it is areas of revolution. And, it's in terms of how the shape is built, it's similar to the volume of revolution, where in the volume of revolution, we had a region rotated about an axis. Here, a curve rotates about an axis, right? For example, if you consider this, let's say, this region. If this region, right, it's not a curve. So if this region revolves about x-axis, it's going to make a ball, right? Region rotates, it's going to create a ball, like a volleyball or a soccer ball, right? Whereas if the curve itself rotates, it's the same ball, but inside is empty. So it's only, a sphere. And it has a surface, right? And now we want to find the area of that surface. Before that, in 9.5, we found the volume of the solid. Now you want to find the area of the surface. Okay. And this is how we're going to do it. The structure is very simple. So consider this curve, right? Between A and B. And, for this case, assume it's y equal f of x, or it could be parametrization. So we could have this one as well. Or we could have a case when x is equal to g of y. So we can talk about all three cases. In fact, if you talk about two, then the other one falls, automatically. So if this rotates, as you can see, it's going to make the surface, only the curve. So I want to emphasize here, only the curve, not the region. If it rotates, right, it's going to make this surface. Looks like maybe a bowl, a pot, but the top and bottom, it's gone. So this is what we're going to do. It's not exactly a straight line. Think about it. If this was a straight line, I'm talking about, this part of the curve. For example, that part of the curve. It's not a straight line. It's not a line like that. It's, a diagonal piece, or it's a curve, okay? So let's zoom into a little part. So let's only consider, the small piece of that. Let's zoom in and make it small enough, right? So it's going to look like that. Now, this guy has a length, right? In fact, let's do it this way. So let's go ahead and rotate it. So if this rotates, this guy. Now, So if it rotates, it's going to make a band almost, right? And think about it. I mean, careful that we only talk about the surface of this band. You know, just imagine you have a wristband and you want to find the area of that wristband. Well, you can go ahead and cut it from somewhere, right? You can cut it and flatten it out, and it's almost going to make a big rectangle, right? Just like the shell we had. Now, the width of this rectangle is exactly that length, which we're going to call, I mean, we call it width, but that's the length of this curve. So this guy is the length of the curve, right? The small element of this curve that we chose. And this guy is nothing but the circumference of this circle, right? So this is the, you know, the circumference of circle. All right. Well, if this guy of remember we zoomed into this guy, right? But this is very small. So if we assume that we pick a point here, which is coming from the function y equal f of x. So if that point is x and y, then we're talking about this length as the radius of the circle we talked about down there. So this is r. Then what's the circumference? It's 2 pi r, right? And but the radius, as you can see, it's the y coordinate of that point. So it's 2 pi y, which is 2 pi in this case because of that equation, f of x, right? Okay. So that one is 2 pi f of x, which is exactly this length right here. Okay. So what's the area of this guy? So the area is going to be this side of the rectangle times that one. So it's 2 pi f of x and then L. In fact, since this length is an element of the curved length up there, let's go ahead and call it dl. So this is dl. Okay. So let me go ahead and erase that one and then call it dl. But we already know what the formula is for the, you know, an element of length. What was it? We had 2 pi f of x. It's a formula we established yesterday. It's the square root of dx squared plus dy squared. Okay. So let me go up there and then write down what we're doing here. Someone opened the mic. You have a question, Reno?
Sorry, 1 second. I'm just reconnecting. It's really laggy.
Okay. So let me write down here that curve is revolving about the x-axis. Okay. So we got to this formula down here. Let me go down there and finish that. And by the way, this was only, let's call it ds as the element of surface area. That's only a small element of that. And of course, if you want to find the entire surface area, it's the integration of ds, which is going to be the integration of 2 pi f of x. And then, so since we're integrating with respect to dx, we can go ahead and factor the dx out of square root. And, it's going to be similar to what we had yesterday. I'm talking about only this piece, right? So it's going to be, think about it, if we factor dx, it's going to be a 1 plus dy over dx, which is f prime of x squared, and then times dx. And I want to emphasize again that this piece is similar to the curve length. I mean, think about it. Let me go up. So this piece of the curve, the one that I circled, with this length, with the length of, what was the length of that? It was 1 plus f prime of x squared, right, dx. Now this rotates about the x-axis. So when it does rotate, so when it does rotate, it goes around the x-axis with this circumference, right? So you multiply that circumference by that piece of, curve at that length, and then you integrate it from A to B. So let me summarize this up there. Surface area. If graph of y equal f of x, x between A and B, rotates about the x-axis, then area the surface of this revolution is, there was s equals to integration a to b 2 pi of x square root 1 plus f prime of x squared under square root and then dx. Now let's go ahead and write down the case for y-axis. It's basically symmetrical, but in that case, you're revolving about the y-axis. So let me write that one down as well. If f of this time x equal g of y, and let's assume y is between c and d, revolves of the y-axis, and the surface area of the revolution is, so it's a very symmetrical, similar formula. So it's 2 pi. This time you're going to have the x as the radius, but x is gy, so you have 2 pi gy, and then here you have g prime of y squared plus 1, and of course you're integrating with respect to y, right? So these are the two formulas we're going to be using. In case of parametrization, depending on which axis you're going to rotate it, right? Either you're going to have 2 pi y in the case of x-axis, or it's going to be 2 pi x. And then your integration with respect to dt. We'll see if we can find an example of that in the Q1. Okay, so that was the formula, or that was the setup. On the exam, I'll give you these formulas. You just have to, figure out which one you have to use based on the problem. Rotation, about what axis. Do you have any questions before we start an example? If you open your mic and ask questions. Okay. Let's do, you know what? Let's do the problem we tried yesterday. And I thought it was a curve length, and see why that integration becomes doable as soon as we make it a surface area. So if I'm not mistaken, it was y equal x squared, right? Yeah, let's do number 12. So number 12 says, find the area of the surface obtained rotating curve y equal x squared. Okay. From it's x squared plus 1, but let's do x squared and see. Actually, this is not the one we did. We did root x, so root x was the one of the integration. So root x, yeah, that one is better. X between 0 and 4 around the x-axis. Okay. By the way, it's not problem. Oh, it's problem 60. All right. Let me draw a graph and see what we're dealing with. So 0 to 4. Okay. Root x is that guy. Now this curve rotates about the x-axis, and as you can see, it's a ball, right? Excuse me. And we want to find the surface area of this ball. Okay. All right. So since it's about the x-axis, the S formula was integration 0 to 4 a to b, right? A to b, 2 pi f of x. Remember, f of x here is the equation of the function root x, and then times the square root of 1 plus the derivative of that function squared dx. And what is the derivative of root x? So derivative of root x, oops, not square. Derivative of that, if you recall, is 1 over 2 root x, right? Okay, that was the setup. All right. So 0 to 4, 2 pi root x. Let's go ahead and simplify that. So we get 1 plus, if we score that, we get 1 over 4x, right? dx. Now, if you remember, yesterday we only had this part of the integrand, and we wanted to integrate that one, if I remember correctly. Am I right, Alex? Donovan? So now you're going to go ahead and integrate this one. So this time, this little piece is going to help us. And this time the integration becomes doable. And you'll see why. Okay. So this is what we're going to do. Pull out the 2 pi, it's constant, 0 to 4. And this root x, push it inside the square root, right? And it would, when it goes inside the square root, it squares, right? So basically this is what's going to happen. You're going to have, so I'm going to send this guy in. If I send it in, you have to square it. And then you multiply 1 plus 1 over 4x, right? And then dx outside. You have a question on that? All right, now let's simplify it. 0 to 4. Since it's square root of a square becomes x, 1 plus 1 over 4x, right? Dx, right? And now let's go to the next page. Let me split it to 2 columns. Zoom by 1%. Okay, so it was 0 to 4. Oh, I forgot to pull out the pi. 2 pi, 0 to 4, under square root we had. So it was x times 1 plus 1 over 4x. So I distribute it, I get x plus 1 over 4, right? And then dx. Now this integration, it does have an antiderivative. And for that, just do a u substitution. So let u be x plus 1/4. Then du is simply dx. Okay? So for that reason, the integration becomes 2 pi. And we can change limits accordingly as well. So if this piece is u, then you have u to the half and then du. And we can find, u based on x, because your limit, your x is between 0 and 4. Now plug 0 into the u, into the x, and you get the corresponding u. So it becomes 1/4. And if you plug 4, you get 4 plus 1/4, that's 17 over 4. Right? Or you can do this antiderivative and substitute u back and then do the same limit 0 to 4 to get the same. So that's 2 pi. So that's 2/3 u to the 3/2. So you do power rule, add 1, divide by the same number. 1/4 to 17. Okay. 4/3. Let's raise that to the 3/2. So it's like you raise it to the half square root. So that becomes 17 root 17 divided by 8 minus 1 over 8. Right? Let's simplify a little bit. Can we? Yeah, we can do some stuff. So 8 and 8, that's a common denominator. With that 4 cancels out. So we get pi over 6. And there's nothing that we can do with it. 17 root 17 minus 1. So that would be the most simplified form of that answer. Do we have any question on any part of this problem? Open your mic, please, and ask.
So why did the limits change? Why aren't they 0 to 4?
Because we changed the variable of integration. The variable of integration was x. Now we're doing u.
So how does that correlate into those limits?
Well, since you're changing the variable of integration, you have to come up with the corresponding limits mean, think about it. How is u defined? U is x, just shift it quarter of a unit,
Hmm.
right? So limits of x was 0 to fourth. Now shift the whole thing 1/4 to the right, right? So if you look at
Yeah.
the real axis, if this is 0 to fourth, that's the limit of x. But based on the definition of u, well, I'm just shifting x 1/4 of a unit. So just shift everything, the whole thing shifted to 1/4 of a unit. So that becomes the limits of u,
Okay.
right? I mean, if you don't want to, you can integrate this. I mean, in this step right here, substitute u back. Like, don't change the limits, right? Just substitute u back. Let me
And
write
then go
down.
ahead and put 0 to 4.
Yeah. So in that case,
Okay.
it would be 2 pi 2/3 x plus 1/4 raised to the 3/2, and now 0 to 4. But if you plug 0 4 and you see it, you get the same thing, right?
Okay, so you just have to plug back in what you had for
Yeah.
you then. Okay,
Yes.
thank you.
Yeah. hmm Anything else?
Nope, that's good. Thank you.
Okay. So let's see if we can do an example of uh, let's see if there's a parameterization. Well, you know what? Let's do number 18. So that's going to create a new brand integration. Okay. Number 18. So same story. That's the surface area generated by rotating. So this time e to the negative x, except x is between 1 and positive infinity. I'll graph it and you see. It's going to look like a, huge funnel around the x-axis. Okay. All right. So here's a graph. First of all, that 1 is going to be 1 over e. So, you can think of that value right there. But at infinity, e to the negative x approaches 0. So it's going to go like that, right? But it just keeps going to infinity. Now, if this rotates, you can imagine what's going to, right? It's going to make a huge funnel that from one side, from this side, just keeps going to infinity. And we want to find the area of that surface. So, questions on the graph? You're going to go ahead and find the surface area. This is f of x. S is integration. 0, oops, not 0. What should be our limit? It's right there. 1 to infinity. 2 pi. F of x. So it's e to the negative x. Square root 1 plus. Take the derivative of that function, square it, and then dx. What's the derivative of e to the negative x? It's minus e to the negative x. Okay. So that's the important one. As soon as you set it up, simplify it and integrate. Do we have a question on that? So that was f prime of x. That's f of x. Okay. So similar to every other integral we do, we pull out the constant part. Let's deal with the inside under square root. So it's 1 plus. All right, I want to square that quantity. It doesn't matter, it's a negative. This sign is not going to make a change, right? Because you're squaring it, so it's going to be plus. But what is e to the negative x? Is it going to be e to the negative x squared? Is it going to be e to the x squared, or is it going to be e to the negative 2x, or is it going to be e to the 2x? I confused the hell out of you. Which one is it? Which one is it? So is it the first one, second one, third one, or the fourth one? The last one. Negative 2x, negative 2x. Let's see more. If you haven't fallen asleep, let me know what the negative 2x. Just because 3 people said negative 2x, everybody keeps saying negative 2x. I'm not saying they're wrong. Negative 2x, only 4 people are awake. Negative 2x. Okay, it's correct. It's negative 2x. So it's going to be e to the negative 2x dx. Right? All right. Now, so that's it. That's the setup of integration. Question is, how do we do it? How do we do this integration? Any suggestions? Improper thing. I mean, yeah, it's improper because of infinity, right? Improper integration. U sub, then by parts. This guy is cracked. You can avoid the U substitution by, you know, putting this guy inside, but it's still U substitution. Yeah, it's a good idea. You know, it's less confusing, you can say. So let's do the U sub and then by parts. Okay. So for the U sub, but remember, every time you have to use a U sub, since this is a definite integration, you have to be careful about the limits. So either make sure eventually you substitute back in the same limit, apply the same limits, or you change the limits accordingly based on the substitution that you choose. Okay. Okay, Reno. So what's your suggestion for the U substitute? Let me write down the integration one more time. So it's 1 to infinity, e to the negative x, and then the square root of 1 plus, and let me help you with this, e to the negative x squared, basically. I'm going to write it like that, and you know what you should let u be. So what do you let u be? Square root and everything in it. So, I mean, let this whole thing be u. Think about it. If you want to do that, the derivative of that needs to show up somewhere. But derivative of that square root is going to be, 1/2 the same thing raised to the negative, which is never showing up there. Could a good one would be e to the negative x itself. Stuff on the root. Yeah, stuff on the root, if you let that be u, e to the negative 2x, if you take the derivative of that, you're going to have negative e to the negative 2x dx. So you still need a copy of a e to the negative 2x somewhere, but you only have one power of e to the negative 2x in e to the negative x, right? So let's go ahead and let this e to the negative x be. So u is an e to the negative x, and of course, du is negative e to the x dx. Okay, and as you can see, these two show up here and here. You only need a negative. Okay, but we'll see. It's going to take care of that. All right. Now, question is, do you want to change the limits now? Because this is what's going to happen. I'm going to write it as 2 pi So it's going to be 1 plus u square. That's going to make a negative du if you write it as e to the negative x dx. So we have a negative and then du. Yeah, Alex, go ahead. Open your mic.
Up here by the top of the screen, you have negative e to the negative x.
Negative
Negative
e to the negative x.
Yeah. So wouldn't
On
that?
top of this. You're talking about
Yeah.
this?
Yeah, because you back down, farther down, you didn't add the negative e, well, the negative back in.
We could, but it doesn't matter, you know, because I'm just rewriting this. You're right. I mean, I could pick a negative, but remember, this negative is being raised to the second power. So it's like -1 squared is 1 itself. So it doesn't matter if you write it as 1 square or -1 square.
Wouldn't that change if you picked the e to the negative x on the outside? You'd get the negative e to the negative x, and that would just cancel what the middle would be.
But then the limits accordingly would change. We'll try that one too. We'll try that one too. You know, in fact, so if you pick negative e to the negative x, in that case, du becomes just e to the negative x dx, okay? So that's what the change is going to make. So this negative here is not going to show up. But in terms of limits, if you change it, if you pick this guy, plug 1, then, so remember, x is between, x goes from 1 to infinity. With this option, u is going to go from -1 over e to 0, right? Because if you plug infinity into this, e to the negative infinity is 0. And if you plug 1 is negative e to the -1, that's 1 over e, so it's -1 over e. Whereas for this guy, with that option, u only goes from 1 over e to 0. There's no negative right here, so it only becomes that one.
No, I get it.
The limits here are not correct, so this should be, you know, u is between 1 over e to 0. But again, this negative is going to be taken care of, you know, by changing the limits, flip-flopping it. But at the end, doesn't matter. Okay.
What about the e to the negative x in front of the square root? Shouldn't there be another one right there?
I
Like
put
a
them
u?
together as du. You're talking about this piece, right?
Yeah.
So those two together go to du. Remember, the negative du has both of them, so we don't have to put another eu over there.
So they just cancel?
Yeah, you can sort of say cancel, but, you know, think about it. What's the equivalent for e to the negative x times dx is negative du, right?
Mm-hmm.
So I'm going to put those two together and replace them with negative du.
Okay.
Okay.
Yep.
Anything else, guys? So let me go ahead and erase these ones. Okay. All right. So should we change the limits now? Whoa, what happened? So let's go ahead and change limits. So changing the limits for that, I mean, we just have it right there, right? So when x is 1, because of this option, remember, because of that, u is 1 over e. And when x is infinity, u is 0, right? Because of that equation. So every time plug 1 over there, u is 1 over e. And if you plug infinity, e to the negative infinity is 0. And so it's going to be 1 over e to 0. because corresponding to 1, we have 1 over e. Corresponding to infinity, we have 0. And now we can take care of this negative because the limits, it doesn't make sense. 1 over e is bigger than 0, but we switch them. And if we switch, the integration changes the sign. So this becomes 2 pi, 0 to 1 over e. Get rid of negative, and now root 1 plus u squared du. Right? That was one of the integration rules, that if you change the limits in a definite integral, the integration itself changes the sign. Goes from positive to negative or negative to positive. Okay. Now we can go ahead and do this integration. But we sort of did this integration yesterday, and I left it for you guys. Do you remember what it became eventually? It became yep, tripsogbatant, tripsogbatant, and eventually became a secant cube, right? Did anybody do that one? Finish that one? So let's see. It's gonna be so for u, let's let it be tan t, right? Then du becomes secant square theta, d theta, and of course 1 plus u square is, let's consider root of that. So let's go to 1 plus u square because that's part of our integrand. It's 1 plus tan square theta, which is square root of secant square theta, and that's secant theta, right? Secant theta. Okay. Now let's substitute. So it's going to be 2 pi. So we said that's secant theta, that's secant square theta, and then d theta. Do we want to change the limits enough? Remember, every time you're doing a definite integral and you do a substitution, you have to ask this question: do I want to change the limits, or do I want to remember that I will, substitute back and do the same limits?
Is it easier to change the limits or to sub it back in and still follow the same limits?
I think it's a matter of preference. I would prefer change the limits just in case I forget, that I have to substitute back and apply the same limits.
But if you go ahead and substitute back in, is it going to make it harder?
No, not at all.
Okay.
If you remember, as long as you remember that you have to do it because you did a substitution, but you didn't change the limits, and eventually you do it, then you're good. You don't have to. Just like I said, it's a matter of preference.
If you go ahead and do the U sub, and do you still have to change the limits even though if you remember to change them back almost when you substitute back in?
No, you don't have to. I mean, what do we get here? This is 2 pi integration secant cube, d theta. So if you know this antiderivative of that guy, go ahead and write the antiderivative, and then right away write things in terms of u, because from here we know theta is tan inverse of u, right? And we can do the right triangle thing and then figure out all the other functions. So write it in terms of u and just apply the limits for u, which is 0 to 1 over e. Does it make sense? Or did I answer your question?
Well, would you have to integrate it first and then obviously have the original limits? Or would you want to change it in terms of x or theta or whatever, and then have the original limits?
It doesn't matter, Reno.
Okay.
Just like I said, if you remember to substitute back, remember, if you do this integral, it's going to be an integral in terms of theta, like the antiderivative of this guy is in terms of theta. If you remember to substitute back and rewrite it in terms of u, then you can just apply the limits of u, 0 to 1 over theta. 1 over e to 0, or 0 to 1 over e.
What about the 1 to infinity?
No, we already took care of that. So we don't deal with that because we already changed the limits. We went from x to u, right? We had x, now we switch to u, and we have already changed the limits for u. So we're good. We don't have to go back to x anymore.
Okay.
Now, same thing here. If you change the limits here, let me write down the limits, for example. So for u, it's going to be 0. And for this one, it's going to be tan inverse of 1 over e. Now that we wrote the corresponding limits for theta, we don't have to go back to u when we do this integration. Right? So with these two new limits for theta, we don't have to go back to u. No, we don't have to. Okay. Let's finish this one. So I forgot what the antiderivative. Did anyone do the antiderivative of secant cube?
I got it, Maddie, if you want me to read it off.
Hold on a second. Let me. This line in the middle disappeared. So let me draw it again. Okay, so let me write my integration one more time. So the integration was a surface, right? So we got to the point where we had this 2 pi, what was it, 0 to tan inverse of 1 over e, secant cube theta d theta. Okay, go ahead, Donovan. So it's 2 pi.
Yeah, times secant theta times tan theta plus natural log of secant theta times tan theta divided
Minus
by 2.
or plus?
Plus.
Minus natural log.
No, plus.
Plus? Okay, so plus natural log of absolute value secant theta plus tan theta and divided by 2. So that's the division. Thank you. So here we have 0 to tan inverse of 1 over e. Okay. So it's going to be pi. Okay. So it's going to be secant. Think about it. What if we plug 0? If you plug 0, that term is 0. And here we're going to get natural log of 1, which is 0. So we're not worried about 0. Let's worry about when theta is tan inverse of 1 over e. So it's going to be secant of tan inverse of 1 over e plus natural log of secant of tan inverse 1 over e plus tan of tan inverse of 1 over e. Okay. That's 1 over e because it's tan inverse. The function and inverse, they cancel out each other. So that's 1 over e. The only piece we need to figure out is this guy. And for that, we can use a, just a trick identity. In fact, so let's just assume tan inverse of 1 over e is, because it's sort of like an angle, so let's call it alpha. That means we're looking for secant of alpha. But secant of alpha is square root of 1 plus tan square of alpha, the identity. But we know what tan of alpha is because based on this, tan of alpha is 1 over e. So this is 1 plus 1 over e squared. That's it. So this value right here is the square root of 1 plus 1 over e, right? Or, you could do the right triangle because tan of alpha is 1 over e. So if this is alpha, opposite over adjacent 1 over e, right? Now let's go ahead and figure secant alpha. Secant alpha is what? It's hypotenuse over adjacent. So it's hypotenuse over adjacent, right? So that's square root of 1 or plus e square over e, which is exactly the one up there, right? These two are similar because if you let e, put the e inside, comes the same thing. E squared plus 1. Just some trick function, you know. Identities and right triangle. Question on that. I want to erase this part. Should I erase this part? No, just leave it like that. I'll leave it like that. So there's just something on the side. Now the rest of this, let me. I erased that whole line again. Let's not worry about that equal sign up there. Okay, so it becomes high, and then square root of 1 plus e square over e plus natural log of, let's make this a bigger parenthesis, 1 plus e square over e plus 1 over e. There you go. We did it. It's an ugly expression in terms of e. But anyway, so it's very interesting. This is the surface area of that funnel. Okay. Infinite length funnel. What's the surface area of that? Is that guy right there. You can tell that to your friend and brag about it. If you have a question. Okay. So, I think class time is over. The rest of the examples and exercises in this section is very similar. So, I'm not gonna assign extra problem. Just work on this problem. Should be.
And you're going to be uploading this as well.
Yes.
And how long does that usually take to upload?
I mean the PDF, less than 10 seconds.
Like the video.
Video, maybe like 5 minutes.
Okay, I'm just asking because like my internet at home is like has been really laggy, so like I got to go back over the video and stuff. But thank you.
Okay. Yeah, you're welcome. I'll just go ahead and as soon as, because I have to close down, I have to leave the meeting on my laptop to be able to get the video, unless it's not gonna put it in the folder that I've assigned to it. But so we can take a break. As soon as I do that, I'll load the video on e-learning, and I come back in 5 or less than 10 minutes for office hours, and if you guys have questions, and we can work on problems. Sounds good?
Yep.
Okay. Question, guys? Let me see. People asking questions. Let's see page 1 real quick. Sure, that's page 1. Is this page 1? Yeah. You want me to zoom in? There's a different formula for when it's parameterization. Dina is asking. I can write that down. Vito, can I go to page 3? I want to make a page and write down 2 formulas for the case of parameterization. Yes. Yes, it's correct. It's going to be the same, but a 2 pi f of x. Except, since it's parameterization, you're either going to have 2 pi x, but x is function of t, so you're going to have 2 pi x of t, or you're going to have 2 pi y of t. But under the square root is square root of dx over dt squared plus dy over dt squared, and then times t. Your integration is with respect. No, it doesn't matter. I mean, it depends on what form of the equation of, the function you get. If you get a parameterization, so you go with the parameterization formula. If your function and which axis you rotate. So if it's a function of x and you rotate it about the x-axis, then you do the first formula we established here. This one right here. And if it rotates about the y-axis, then you use the second. So it matters, it depends on which axis you rotate. And of course, it could rotate about other axes, parallel to x and y. But, I think the book is not talking about it, so I'm not gonna that one. Although it's similar, like area of revolution, you rotate the region about x equal 2 or y equal -3. It's the same. But let's only focus, on the simple cases. Master that. And as long as you set it up correctly, the rest is into. Okay, so let's finish this session and come back in 5 minutes. And in 5 minutes, I'll make a PDF out of this, put it on e-learning, video on e-learning, come back for office hours so you get questions. Talk about it. Okay? So I'll see you guys in 5 minutes.